Okay.
So welcome to our seminar. I'd like to start by welcoming Professor Tamara Bartadim, who is in Kiev now, and who is attending our seminar. So I talked to her 10 minutes ago. She told me that she has a good internet connection in Kiev, and now the situation is calm, and then she opted for attending our seminar. So welcome, and thank you for being with us. And I would also like to introduce our speaker today, who is a young mathematician from China. This is Junyi Liu from Tsinghua University. So Junyi received her PhD from the University of Southern California in 2019, and continued there as a postdoctoral researcher in the group of Zhang Xipang. She moved in March 21 to Tsinghua University, which is one of the top Chinese universities. So in Beijing, of course, but Tsinghua is a famous institution not only in China. Junyi is working on particularly on topics in stochastic programming, on non-monocle optimization. She's very much interested in applications to machine learning, to risk measure minimization. So thank you for accepting our invitation. So thank you to the audience for being with us today. So Junyi, you have 45 minutes for a talk.
All right, thank you, Radu, for the introduction, and thank you very much for having me here. So let me first get this full screen mode. Well, the sharing is paused.
Yeah, so we see a black screen. Probably it's better here to switch back and.
Okay, then I'll
maybe you were sharing a specific window and not the whole screen.
But probably don't need a full screen.
Yeah, this is fine.
This is fine. Okay.
Yes.
All right. So this talk is based on the joint work with Zhang Xipang, and who is here, and also Professor Yin Cui from the University of Minnesota. And the topic of this talk is about solving the non-convex and non-smooth compound stochastic programs with some applications to the risk measure minimization. Well, so this is the outline here. At the beginning, we will introduce the setting of the compound stochastic program, and we will discuss several applications of these kinds of problems in the areas of risk measure minimization. And for solving these kinds of problems, we design a stochastic majorization minimization algorithm, and we established the almost sure convergence to the stationarity and also the probabilistic error bounds for the stopping rules. And at the end, I will introduce some extensions of this compound stochastic program to the risk-based robust statistical learning problems, and also show some numerical results here. So here, this is the setting of the compound stochastic program. The basic feature of the stochastic program that distinguishes from the standard stochastic program is that the objective function has the two-layer or multi-layer of expectation functions that composited by the some functions phi and psi. And here we address this kind of two-layer expectation functions in theta, and the random functions g and f here are potentially non-convex and non-differentiable. And they are composited by the two deterministic functions, the phi and psi here. And they are assumed to be isotone and convex functions. So before going to the algorithm, let me first introduce several applications of these kinds of problems first. The first is the elementary risk deviations, such as the variance, which is the expected square deviation from the mean, or the expected absolute deviation from the mean, or the semi-deviation from the mean. This kind of deviation has the two layers of expectations in the objective, and also for the latter two deviations, we can find that the inner functions phi could be the non-differentiable functions. And also this could be extended to the generalized risk deviations. So let me introduce several backgrounds on the risk measures here first. Suppose we have a random variable z with the cumulative distribution function f of z. Then var is the smallest value z such that the cumulative distribution is greater or equal to alpha. And for the var, we have this kind of the inverse, which is the probability of accidents. It means the probability that the random variable is greater than some threshold tau. And so informally, we can see the 1 minus POE is the inverse of the var here. And based on the var, there is a famous risk measure that is called conditional value at risk, brought out by Rockefeller and Ruasif. And it takes the average over the tail distributions so that it could be more robust to the data points. And also it has a nice optimization structure here. It is the value function of the single value convex program here. And similarly, we can, there is Rockefeller and Roy-Sett introduced this bar for probability of accidents that is defined as the inverse of CVAR. And also it has this kind of minimization formula that is the minimization of a single value convex program here. So, and also the Bento and Tabot has recognized that CVAR is actually a type of utility-based optimized certainty equivalent. So that's the, as you hear, the OCE is actually the soup over a concave program with a concave and non-decreasing utility function U. And based on these kinds of risk measures, we could have this, the generalized deviation minimization. For instance, we could have this OCE-based deviation problems, that is to minimize this kind of the minus the OCE of the deviation. And with this minimization formula of the OCE, then we can have this kind of compound structure here. And also with the BPOE, we can have the BPOE-based deviation minimization. So, and with the minimization formula of BPOE, we could have this kind of compound SP as well. And we could notice that in both of these two compound expectations, there is only the inner composition functions, but also that the inner composition function phi could be a non-differential functions, and the random functions G and F could be the non-convex functions. And the next question, the next application is this cost-based multi-class classification. Suppose that we have a medical diagnosis classification problem, and there were 5 levels of disease condition that we want to detect. The higher number represents the worst condition. So based on the gap between the true level and the classified level, we could construct several groups of arrows so that the arrows in each group can result in the similar cost, but the cost of the arrows among different groups could be significantly different. And with this kind of cost-sensitive idea, we have this the classification model. Suppose we have the attribute and the class pairs X and Y represents the label of the individual, and the attributes is the for each label. for each class M, there is a scoring function parameterized by mu of M. And then attribute X is classified into the class J if the scoring function of the class J is the maximum among all the scoring functions. And the idea here is to estimate the parameter mu such that the misclassification error is minimized. So here we have several types. We have this set of misclassified label pairs, and suppose we could separate these arrows into S groups, and in each group, the arrows is associated with an individual cost in learning the classification. And ideally, we want to minimize the misclassification errors. However, these kinds of the probability of accidents is a discontinuous functions, and this is very challenging to be optimized directly, but it could be approximated by the buffer probability of accidents, which considers the tail probability distribution. So in this way, for each group, we consider the maximum of the POE of the misclassifications, and then we took the summation over all the groups. And with the minimization formula of the buffer probability of accidents, we could have such kinds of compound SP program. And we can notice that inside of the expectation, the random function F here is actually a non-convex and non-smooth function, even if the scoring function is a linear function. So these are several applications that motivates us to study this kind of non-convex and non-smooth compound SP. Well, in the current literature, there are 2 lines of research that have been addressed the compound stochastic program. There is a line of research that addresses the asymptotic and non-asymptotic statistical analysis of the sample average approximation estimators, assuming that the global optimum of the SA model can be obtained. And for the algorithms, there is a line of research that assumes that all the functions are smooth functions with the Lipschitz gradients, and they propose this stochastic gradient-based algorithms for solving these kinds of problems. And until recently, that Rosinski has proposed this kind of stochastic generalized subgradient-based algorithm for solving the non-smooth and non-convex multi-level composition optimization. Here, the multi-level means that there were multiple expectations composited in the objective function. However, for our compound stochastic program, it is unclear that how to obtain the generalized subgradient for such problems. And also, due to the compound structure, the sampling strategy is also the challenge part for designing the algorithm. All right, so here, the idea of solving this problem is to construct the stochastic majorization minimization iteratively in the algorithm. And here, the idea here is that we want to construct the surrogate family for the random functions G and F. And this surrogate family of functions consisting the function that satisfies several conditions. The first one is the touching condition, and also the majorizing condition, meaning that the G hat is always the upper bound of the original function G. And also the G hat, the surrogate function, is the convex function and we have technical assumption on the uniform outer semi-continuity for the convergence proof here. So besides the surrogates, we also need a sampling scheme that we incrementally discretize the nested expectations with two independent sample sets. So combining with the surrogation and the sampling, we have this sampling-based surrogate objective. And remember that we assume that the deterministic function phi and psi are all the convex and isotone functions. So the surrogate objective function they had is convex functions in X here. And SMM algorithms, well, before the algorithm, Amy introduced a class of problems, the DC functions, as how to construct for the DC functions, for the difference of convex functions G, that we can linearize the concave part or the second component functions to construct a family of convex surrogate functions. And this is the way how we construct this surrogate families. And so this is the main iteration of the SMM algorithm. So at each iteration, given the current iterate point x mu and the current sample sets, the two independent sample sets, C and eta, we first generate a set of new samples independently from the historical samples with the size delta mu. And together with all the historical samples and the current new samples, we construct the sampling-based convex surrogate function we had. And then the next iterate point is the proximal mapping point with respect to this V hat. So for such sequence X mu, the convergence or the convergence property of this sequence X mu really depends on the rates of the sample size in mu here. And in theory, we prove that if the sample size in mu has this kind of polynomial increasing rate for any alpha greater than 1, then every limit point x mu, x infinity of that sequence produced by the stochastic majorization minimization algorithm is actually a fixed point of the algorithmic map. And of the algorithmic map of the surrogate function on the expectation level. And here the case,
I have a question.
Yeah, sure.
Yeah, it's just a little hard to track all the notation so quickly. That do you start with a new sample each iteration, or do you add to the sample you have already?
We add all the newly generated samples to the historical sample sets.
Okay. Okay.
Yeah.
So you just
So
keep
it's a kind
constantly
of
growing.
accumulate.
Yeah. Okay.
Yeah. Yeah. So this is a accumulation sampling scheme, so that the sample size in mu here represents all the samples that have to be generated at the iteration mu. And this increasing rate means that at each iteration, the newly generated samples size has to grow to the infinity. So if the newly generated sample size is only constant, then mu is just a linear rate, and we request a little bit stronger to be a polynomial rate for alpha greater than 1.
And you move, but you move this x prime, so your approximation keeps changing, right?
Yes, yes. Yes. this X prime or the X mu here, it keeps
Right.
updating, yeah, along the algorithm. Okay. Okay, so, and this is the convergence property of the of the limit point of that sequence, and the key steps of the proof is to establish a decent property of the sequence of the objective values with some stochastic errors. And then we require the sample size to increase at such polynomial rate so that the accumulation of those stochastic errors could be finite with probability 1. And this is how the requirements of the sample size comes from. And here we only state that the X infinity is a fixed point of the algorithmic map by relationship of this fixed point to the stationarity of the original problem actually depends on the structure of the function f and g and also the constructions of the surrogate families. And there are two examples here. It says if f, g are smooth functions with Lipschitz gradients, or if f and g are differential convex functions, then the fixed point property could be related to actually result in the directional stationarity of the original compound stochastic program. Okay, so this is the convergence of this SMM algorithm. And next question is the how should we stop, or when should we stop the algorithm? In stochastic programming literature, the existing approach to assess the solution quality include bounding the optimality gap or testing the KKT conditions. However, for such non-convex problems, it is not practical to obtain the global optimal solutions. So the optimality gap is not practical here. It's not applicable here. And also because the problem is also the non-smooth and so the KKT conditions may not be applicable as well. And this motivates us to consider to establish kinds of error bound such that for all the test vectors x hat, for instance, we can say that the distance of x hat to the stationarity is actually bounded by some computable residue with high probability. And the high probability is here because this residue should be computable. So it actually is dependent on some discretization. And then if we have such error bound, then we could see that if the residue is small, then the distance of that test vector to the stationarity is small with high probability. And this is the idea here. And so we construct such the computable residue by using the algorithmic map. Here, this V n hat is just the sampling-based surrogate function that we had constructed before. So for test point x hat, we could say if the sample size n is large enough, satisfying that condition, then the probability of the distance of x hat to the set of stationary points here should be bounded by the sample-based residue plus the epsilon with this probability 1 minus alpha. And here, we should notice that there were several conditions for such error bounds. The first one is that the S here denotes the set of Clark stationary points, and actually it could be extended to any stationary points that it's necessary condition for the global optimality. And so we assume that the sets of Clark stationary points belongs to the fixed points of the algorithmic map. And the second one is that there is a local error bound of such problem. And the third one is that the surrogate function that we constructed has the upper bound of the proximal term. And with these three conditions, then we have such a probabilistic stopping rule here. All right, so the next is the extension of this compound SP to the robust regression model. This is the extension because the compound structure that we will address is a little bit different. It's actually quite different from the one that we addressed before. It has this kind of value function composition structure. So here we have this robust regression model, and the classical one is the robust M estimator that's replaced the standard square loss function with some robust loss functions such as the L1 loss or the Hilbert's loss. And another one is this trim M estimator that is to minimize the average of H smallest losses. And it has been shown statistically that the trim M estimator has the better statistical efficiency and also is more robust to the outliers. However, the computation of the trim M estimator has been has always been computational challenges. First of all, even for the linear regression model, the trim M estimator actually is still a non-convex and non-smooth optimization problem. So in the statistical literature, there has been several heuristic algorithms that have been proposed to solve this problem. However, the size of the subproblems there is in the order of the data size, and the probability of the obtained solution is not guaranteed. And recently, Arafkin and Davis proposed a stochastic proximal gradient algorithm by reformulating the problem as a non-convex optimization problem with a simplex constraint set under the smooth conditions of the loss functions. So basically, they transpose the simplex constraint set is actually corresponding to the data points. So the number of variables is also in the same order of the data points. And they assume this loss function is smooth. So they propose the proximal gradient algorithm here. And we took a different perspective of the trimming estimator, that is to utilize this interval C-var risk measure. This kind of risk measure was proposed in an unpublished technical report by Asaf and his co-authors. Basically, it took the average of the random variable restricted to the two value at risks, so that it could exclude the right tail and left tail distribution simultaneously. And with this kind of risk measure, we could construct a robust regression model. And we applied the in-C-var to the overestimation errors and the underestimation errors separately, and so that we could excessively exclude excessively large or small residues in model fitting, and also the overestimation and the underestimation errors are evaluated with the asymmetric levels and asymmetric weights. So for such problem, the regression function f could be a non-convex function. It's actually a difference of convex functions that could cover the linear regression model, the piecewise affine regression model, or the two-layer neural network with the ReLU activation functions. Well, so for this parameter estimation problem, we could reformulate, this is another class extension. We could also utilize the in-CVAR risk measure to the classification problems here with the hinge loss function or the logistic loss function. And also the discriminant function could be any difference of convex functions. Well, so now let's move back to the in-CVAR based robust regression. We could reformulate the loss functions into the summation of two CVARs and minus two CVARs. And so with the minimization formula of the CVAR risk measure, then the loss function L is actually the difference of two value functions. And each value function is the minimization of a jointly convex program, stochastic program. Okay, so here, at this point, we could say that there is a composition structure in the objective, but it is composited by the value functions. So that is the main distinction from the compound SP that we have addressed. Okay, and so we know that the value function of a jointly convex function is still a convex function. So the loss function here is the difference of two convex functions and denoted by U and V here. And the parameter estimation problem is actually a difference of convex program. So in principle, if we have a given set of data points, then we could solve such program by the classical difference of convex algorithm. However, such deterministic algorithm may not be practical when the number of data points is too large, or even we want to tackle these problems at the population level. So this motivates us to study the stochastic difference of convex algorithm. And such algorithm is actually a special case, or the special case of the SMM algorithm that we have addressed. So the basic idea is that we want to combine the sampling and the convexification. So for the first component function, for the first convex component function mu, we just utilize discretization of using the subset of samples of size and mu. And the second component function is a little bit troublesome because it is convex, because there is a negative sign before the convex function v, so we need to linearize such function with the sampling. And the linearization is obtained by using the subgradient of the discretized function v. And so combining this sampling and linearization, we could have this kind of SDCA algorithm. Well, this kind of algorithm has the similar results that says that every accumulate, as long as the sample size and mu satisfy the polynomial incremental rates, so that any accumulation point of the sequence is a critical point of the parameter estimation problem almost surely. And we should notice that this SDCA algorithm acquires a stronger sample size requirement than the SDCA algorithm in this paper by Letai and his co-authors, because that we have this value function structure in the INCVAR-based robust regression model. So the sample averaging or the discretization is a biased estimation, so that we need a stronger sample incremental rate in order to control those stochastic errors. Okay, then I like to show you several preliminary numerical results of this SMM algorithm. Here is the OCE of deviation optimization problem with the exponential utility functions here. So with the exponential utility function, we can find that the objective function is the smooth function. And so we could compare our SMM algorithm with the NASA algorithm from this paper by Gadimi, Razinski, and Wang in 2020. According to them, this single timescale stochastic approximation method is the most efficient algorithm among the other stochastic approximation methods. And here, we can observe that the SMM algorithm actually converges with just several or thousands of iterations, and we have this kind of NASA algorithm that shows that the NASA algorithm is actually a little bit sensitive to the initial points. So for such problem, the global optimal solution is around 4, so that when we restricted the initialization range to be the interval 3, 5, then the results or the convergence is much faster than the NASA algorithm with the initialization range in 0 and 8. And also the variance of NASA is relatively more volatile than the SMM algorithm. And of course, the NASA algorithm is only based on gradients, so the running time is much better than SMM. And SMM, in every iteration of SMM algorithm, we need to solve a subproblem, solve a convex subproblem. And that is the main reason that the running time is much longer than the NASA algorithm. But it is possible to consider the 2-loop scheme for the SMM algorithm in order to improve the computational efficiency. Well, and this is another numerical results for the robust regression model here. And suppose that the ground truth model is this kind of piecewise linear functions phi. And we compare the results of the INCVAR-based robust regression estimator to the Huber estimator and ordinary least square estimators. And among all these comparisons, that INCVAR can give us the best mean absolute estimate errors comparing to Huber's and OWOS estimator. And also the running time is considerably acceptable. Okay, so Okay, so there should be another table here, but it is not. So we also compile this SDCA algorithm with the deterministic CA, and this running time of SDCA is about 30 or 40% smaller than the deterministic DCA algorithms. All right, so in summary, that we can say that non-convex and non-smooth compound stochastic programs have many applications, including the generalized deviation optimization, the cost-based multi-class classification, or the robust statistical learning. And the extensions may include multi-layer compound SP and also the conditional SP. The conditional SP means that the inner random function could, or the inner random variable could be dependent on the outer random variable. So we use conditional expectation as the inner component functions. And we developed the stochastic majorization minimization algorithm based on the Stargate family of functions for obtaining the fixed point of the algorithmic map. And this fixed point of the algorithm map could be related to the stationarity depending on the construction of the Stargate family of functions. And also we established a stochastic error bound, which theoretically justifies the probabilistic stalking rule for the SMM algorithm. Okay, so this talk is actually based on the following two works, and with Professor Zhongxi Pang and Ying Cui. All right, so this is my talk, and thank you very much for being here and looking for any questions.
Thank you, Junyi, for an interesting talk. Very, very nice results. Are there any questions?
Hello, this is Tim Wei-Meng from Brown. Can I ask you a question?
Sure.
Yeah, okay. Can you go back to the main algorithm? So in your problem, do you assume those two functions phi and psi are convex or not?
We assume it to be convex and also isotone functions.
Okay, so that means v hat here is also convex, right?
Yeah.
Okay, got it. So and how did you solve this step 3? Just
well, yeah, so we do not elaborate the inner loop for solving it, but in numerical results, we only use some solver to solve this kind of sub problems.
Okay, I see.
Yeah.
So, okay.
So basically, you may consider this step 3 could be extended to be an inexact computation. So it may not need to, it doesn't need to be the global solution of this sub problem, but it could be an inexact solution so that you can design an inner loop of scheme for obtaining an inexact solution here.
I see. Okay, thank you.
Thank you. Professor Rudziński?
Yeah, maybe I have a remark here. So the main idea here is to create increasing samples and then use them to construct an approximation of this multi-level problem. Okay, so then basically, and you have this, as far as I understand, this maximization, minimization, some functional objects that approximate the function from above and below, and you get convergence to the result. So I wanted to say is that in your approach, in my opinion, it is possible to obtain a rate of convergence for your solutions. And for the objective value for sure, and maybe for solutions under additional regularity conditions. So there exists a statistical theory, the Donsker theorem about random functional objects. And this has been extended. You actually quoted one of these papers. This was a paper of Darin Kadencheva, Spiridon Penev, and me on using in the nested version extension of this Donsker setting in the nested version to such a multi-level optimization. And this is perfectly fits to your setting. So your approximate functions, which use these samples, should converge at the rate 1/square root of the sample size as functional objects. The conditions are rather weak because Hadamard directional differentiability is required. So it's not so much required, okay? And then you would be able to present the rate of convergence. I believe this would be big strengthening of your approach. Did you think about that? Because I think it's a low-hanging fruit.
Yeah, sure. Yeah, I think that this is a great question. That convergence rate is the one remaining issue, or is one of the unsolved issue that of this kind of algorithm that I've been thinking about of this convergence rate. So actually, the first thing of defining convergence rates is to what is the measure that we want to use to quantify this convergence rate. So for such problem, that's the of course we cannot use the function value, but we need to quantify this distance of this point to the set of stationary points, and this is a one reasonable measure. And another thing is that currently we have been looking at utilizing the distance of successive iterates and to quantify the rates of the successive iterates. And also in quantifying these rates, we need to actually consider the inner loop algorithm, at least I think, because for instance, if for a fair comparison with those stochastic approximation algorithms that you have developed, I think we need to elaborate how this iterate x mu plus 1 is computed. And then we need to compute the overall complexity for the fair comparison. Yeah.
Oh, yeah. Thank you.
Yeah, this is the ongoing work, but it's not ready yet. Yeah.
Thank you. So Junyi.
So Andre, that's a great question. Okay, so and I think that Junyi has pointed out some of the challenges, okay, and possibilities. So I want to add that there are a couple of things. We always interested in rate results, okay? But even in the deterministic case, okay, so you take away all the stochastic things, and then even for a deterministic, let's say DC program, okay, and then you apply just the standard DCA. Getting rates for that, I think, is not quite known, okay, and so that's the first thing. So I think that it would be good to get the rate results, but I probably would start with even the deterministic problem. Okay, so that's the first thing. The second thing is, I think that somehow, by the way, your suggestion is a great research direction, Andre. Okay, we definitely will try to follow that. The other point that I'd like to make is that the surrogation, the gap of this surrogation, the head functions. I think the rate result should depend on how good your head functions, the gap between the surrogate functions and the original functions.
Yeah, of course. Yeah.
I think that those things should come in when we study the rate results. But again, I think that your reference probably could be useful as a first step to try to look at that.
Yeah.
But it's a great suggestion, and I'm not fully convinced that it is It's probably a midway hanging fruit, not low hanging. It's
Yes, maybe
doable.
not working.
Yeah, but not just that.
Yeah,
but,
this
but it's
was
a great
supposed to be a
suggestion.
joke, okay, but it's
Yeah, great
Okay.
suggestion. We can certainly look at that. We love to get rates. We love to get rates.
I agree. So thank you, Junyi. Got other questions? So Junyi, I have a question.
Yeah.
So what I like a lot the OCE model. Yeah. So the OCE model is covering many risk measures, including.
That's Mark Tabor. Is Mark
Yes,
is here?
I know.
Mark?
I know. And what I like is that one can take different function used. These are just real functions and get different risk measures, including conditional value at risk. So this is also covered by OCE. But then the question is, since the OCE model is an ephemeral value function, so the question is, if you want to use it for, let's say, for DCA, you will need the subgradient of this construction to have an idea how to calculate it. So I mean, so you're minimizing X, and then you can see, you can see the remaining part as an ephemeral value function in eta, and then you need the subgradient if you want to apply DCA.
Yeah, it's not exactly the DCA. So here, we have the OCE.
No, sorry.
Right?
So let me say it again. So if you want to apply DCA for a function which is which is just the difference of two such functions. So you can replace the conditional value at risk by an OCA, and the same for the other one. Yeah, so just generalizing, making another step. And then in order to evaluate the subgradient, you will need a formula for a differential of this OCE function. And this subdifferential should be written in terms of subdifferential of U. Then you get plenty of nice subdifferential formulas.
Yeah, right. So here we then that really depends on the property or the structure of the utility functions. For instance, for the piecewise utility functions, that is doable.
Yes.
And but may be complicated for other complex utility functions, right?
I'm not sure.
So,
I mean, I guess there are many options there. You can do it for many such functions, utility functions.
Yeah.
I agree. Yeah. But then let me make another suggestion. Then for DC problems, there are algorithms which combine a proximal step for one function with a subgradient step for the other function. So you have a positive part, the negative part, in such a DC model. And there is, DCA is very standard, but there are some follow-up schemes which just combine proximal steps with subgradient steps. And why I'm saying this, in the proximal step of an OCE for these functions, there are exact formulas.
Yeah.
And it just makes sense, to make a step, let's say, further, not to stay only with DCA, but also to try other algorithms for minimize or for solving the minimization of such functions.
Yeah, that's a great suggestion.
And sometimes it's easier to calculate proxy operators than to look for subgradient.
So in principle, Radu, you can do a lot of things. Basically, all you need is a convex surrogation, sort of majorization.
Yes.
And I think if I understand you well, what you should suggest is a special case. You special type of majorization, because you for the positive thing you use the proximal gradient map, for example, and then the negative part you use the standard subgradient.
Yes.
And I think the resulting thing will remain a majorization function, or what we call surrogation function. And I think as long as you have such a surrogation function, I think the thing should work. But certainly something that is explicit form. But I think in
Junyi, I have the impression. Okay. Is there a problem with the connection of Junyi? Yes, I guessed it. Yeah.
Yeah.
So he lost connection.
Yeah.
Okay. Yes. Junyi, can you hear us?
yeah,
Okay.
I'm sorry.
Okay.
Yeah, so anyway, I think that's a great suggestion, Raju.
Okay.
Something more to work on.
Yes. No, but so yeah, one should at least try to use also these methods which combine proc state with some radius
Sure.
states. Yeah. So this is, I mean, Junyi is a young colleague, and yeah, I mean, there are many topics to address in the next years, in future. Very good. So are there other questions?
Yeah, just a short question. It's just, so all the test problems you tried are fairly small, right?
Yeah, of course. Yeah, yes, indeed.
Yeah, so this
Let
is,
me see here.
This is the scale is very small
yeah,
currently.
yeah. So the question is, there are obvious questions. How does it scale? And in the big problems, like how, I mean, this is totally going to be totally problem specific, but what the in the big problems, like, how good are these critical points? You may have issues where, the little problems, like the critical points are almost always optimal, but in the big ones, maybe not,
Yeah, so for instance, for the robust regression that we have tested, actually on the real data of the of like 10 variables, but it's still in the small scale. So we haven't tested on the large scale yet, but that's definitely should be a next step to see the actual performance in the large scale.
Yeah, and you may be, I mean, your sub problems look a lot like a bundle method, right?
Yeah, so
yeah, it's like a quadratic penalty, and then you have some like linear, could be more complicated because the phi and the psi could be nonlinear, right? But it's sort of bundle method like, only it changes more.
Right, yes. So the phi psi are, yeah, for those like generalization deviation problems, they are potentially non-smooth. And the piecewise functions, for instance, that they may be cause some difficulty of this solving the subproblem.
Yeah, but it may become, the central issue might become efficient solution of this step 3, or approximate solution of this step 3. Because this will grow, also it has to keep growing.
Well, you mean the as the iteration grows, the sample size grows large.
Yeah.
But at least, yeah, it's also part of because of the small scale problem that we have considered. So the algorithm converges just after several iterations. It's relatively a small number. Yeah.
Yeah. Okay. But it's still very interesting,
At least I think it's interesting to compare this kind of surrogate idea with those classical stochastic approximation idea. Yeah, it's like we utilize this accumulation sampling scheme, but it could yield the more stable results, at least, I think. Yeah, but the computation of each subproblem could be more costly. That is kind of trade-off.
I mean, it may be possible as these subproblems grow, it may be possible to kind of, if you have constraint, you know, basic, what are effectively constraints once you've reformulated it into something a solver likes that aren't binding. You know, you can kind of throw them out and just test if they're violated, and then you could keep this problem from growing and growing, you know.
Oh, of course. Yeah, yeah. That's a good idea. We should
Okay.
definitely, yeah, think about that.
Okay, thank you.
Yeah.
Thank you very much. Thank you. Are there other questions? Comments, remarks? So then let us stop here. Thank you, Junyi, for this talk. So for a very consistent discussion. So just like to announce that we will post the videos and the slides on our website. And to let you know that our next speaker will be, so we will go further to the east. Our next speaker will be Bruno Lorenzo, who is in Tokyo, I guess, yes. And to tell you that, of course, our thoughts go to our colleagues in Ukraine. I'd like to wish you a great week and see you next Monday, hopefully in a more peaceful world. Thank you very much. See you.
Thank you.
Bye.
Bye-bye.